Today's lecture, we're going to keep talking about machine learning. And we're going to talk in particular about moving from linear modeling and linear, kind of purely linear algorithms to nonlinear ones. Though I should say, the algorithms we're talking about today are still actually of the nature, or they still actually go by the name of linear algorithms. And I'll talk about what we mean by that. We're actually going to get nonlinear behavior, not by changing the algorithm, but just by adding features that are nonlinear in the inputs to get nonlinear behavior. And so we'll talk about that a lot. And in doing so, we're actually going to introduce a lot of other topics in machine learning, kind of by way of example. Things like cross-validation, like regularization, and like the evaluation, how we actually report our results from machine learning algorithms. So we'll touch on all of these things. I don't think quite all today, and I think actually this lecture deals with a lot more than that, or this set of slides will eventually deal with a lot more than that. This is sort of the basic content of today. Before I get to that, though, we have to finish up a few slides from last time still on classification, but I want to make some announcements as well. So the tutorial, my example, finally will be released this evening. Sorry again for the delay. This is going to be the tutorial on GIS systems. There's a little bit of a trade-off between trying to be a little bit broad, but also keeping it within the 2,000 words that is your limit for the tutorial. I didn't want to violate those limits in my own work. So we're actually chopping it down a fair amount to make it shorter. I don't think you'll miss out too much of the content. I think mainly it's just me being verbose and sort of rambling for a little while. So I cut down some of that, and we'll release it this evening. Class project assignments also, as is indicated on the website, those are also going to be released today. So we're going to have a description of the class project, what the different deadlines are, what the different expectations are, and hopefully that now people will have a lot more sort of solid sense about that. The one thing about this, though, which we're still a little bit unsure of, is about the final exam. So as everyone probably knows, we have no final exam in this course, but I did say on the first day of class that we were going to have the final project presentations during the final time. We just happened to get one of the absolute last final times of the entire registrar's schedule. It's like a Sunday, December 18th. And a lot of people have kind of wished they could go home before then. So we're going to have a Piazza poll to see if people might prefer a different environment for that. Either doing it somehow not in a big auditorium, but online or something where you're still required to watch them, or some other way. We're going to release a poll on that, so bear with us a little bit. We don't want to force everyone to stay here like 3 extra days if you're going to leave a lot earlier otherwise. And lastly, on Piazza, one thing that we're seeing a lot is people are starting, even if people do reference past posts, they're starting new posts rather than replying to old ones. As much as possible, reply to old ones rather than starting a new one. If your post fits with a similar topic, just reply as a follow-on to that. That lets us kind of contextualize what we're replying to without having to figure out, from anew what people are talking about. So try to do that. Any questions about these things? All right, in that case, let's jump back to classification. So when I ended last time, we talked about support vector machines, which I'll just briefly highlight again. So a support vector machine, as you may remember, is the combination of, it's the classical machine learning optimization problem, minimizing a sum of losses plus regularization, where we minimize the hinge loss. And the hinge loss is an approximation to or it is in some sense an approximation to the 0-1 loss. But here, yi is going to be a binary -1 or +1 label, and x is going to be some vector of input features. And this is a loss, which sort of measures, how bad are we, how confident are we when we get things wrong, and how much we want to penalize ourselves for getting things wrong by a certain confidence, where our confidence is indicated by theta transpose x. That's the hypothesis function. So this is a support vector machine. Now again, if you've seen it before, you've probably seen them in terms of sort of a geometric interpretation, which is, of course, the same thing as this, but this is a different way of looking at it. I think one which kind of captures the similarity between it and other algorithms a lot better. And we can solve this. We can solve this optimization problem by gradient descent. So this, as I illustrated briefly last time, was the gradient of this objective function. And so by taking small steps in the gradient, we can actually find a good value of theta that gets low loss here. And if we plot this over, we plot the solution here. This is our breast cancer data set. So these are mean area of the cell, mean number of concave points of each cell. And these are a plot here that shows for these two features, what is the label? Is it a benign or a malignant tumor? And this plane here is the separating boundary between the positive class and the negative class when we solve this with a support vector machine. And similarly, we can also look at how these objectives progress over time. So this is a plot of loss versus iteration number. This is a plot of the error versus iteration number. I said this last time, but again, I want to emphasize that these things are different and they're both important. So oftentimes, we can't actually minimize the loss we care about. If we care about error, that is very hard to optimize, right? That's the 0-1 loss, and it's hard to optimize. But we want to observe how that progresses over training along with the error we're actually optimizing. So in this case, we're actually optimizing the hinge loss here. We see that nicely decreases kind of smoothly. It's what's called a convex loss function. So we actually can find the global solution of this function. And we can see how that evolves as well as how the mean average error evolves per iteration of gradient descent here. OK, so that's where I ended last time. Were there any questions on that? I know I was going kind of fast by the end there. But any questions on this first? OK. If there are no questions, really, I'll move on to logistic regression. So this is an algorithm that actually predates machine learning, like least squares. It predates machine learning, the term machine learning, by a long time. But I will formulate it and phrase it as a machine learning algorithm. So logistic regression is just solving, again, the canonical machine learning optimization problem, where now, instead of the 0-1 loss, we use what's called the logistic loss. Logistic loss is just the log of 1 plus the exponent of the class times the hypothesis function there. So I showed you a few slides ago. I showed what that looked like. I can bring it back to highlight it, though. Here we go. See, logistic loss is this one in green here. So again, if this term here is really big, that means we are predicting the correct sign of our example, and we're very confident because we have a high hypothesis value. Therefore, this thing, oh, I didn't edit my slides. I thought I did edit these slides. I'm going to just edit it right now, you know. It's supposed to be a negative sign there, so I'm just going to fix this right now instead of having it a problem again. All right, much better. Sorry about that. I should have just done that last time. I don't know why I didn't just edit it last time. If this thing is a really big number, the negative of this thing will be a really small number. And so the exponential of a really small, a really large negative number is almost 0. And so this is about equal to log of 1. In other words, it's about equal to 0. But always a little bit more than 0 because this thing's still always positive. On the other hand, if this is a really big negative number, then x of this thing will be a very big number because it's x of just, you negate it, so you have x of a very big positive number. And this will be approximately equal to just the thing inside, right? Because the log, the 1 kind of doesn't play a role there, and so the log kind of dropped out. So this is kind of a smooth version of a function that becomes linear as it goes this way, as you become more confidently wrong, and goes to 0 as you become more confidently right in our classification space. And it's nice because unlike, say, the hinge loss, this is actually a smooth function. So it's differentiable everywhere. It's actually, you can differentiate it as many times as you want. You can keep differentiating it. So you actually can apply other higher order optimization methods if you want. But it's kind of a nice function for that reason. So this is the logistic function. And when you combine it with minimizing this sum of examples of losses over all your examples, you have a logistic regression algorithm. The gradient descent update for this algorithm, which is not actually the standard way people solve this. People actually often solve it, because you can keep differentiating, people actually often solve it with a higher order method called Newton's method. But we won't talk about that in this class. You can solve it. And actually, for large scale problems, you often want to still solve it this way with gradient descent. But gradient descent here just takes the following form. I won't derive this, but you can imagine how that might pop out. By the way, there are plenty of typos in the slides, but this is not a typo. There's no negative sign there. The negative sign goes away when you create the derivative. So see if you can derive that. There could be typos elsewhere in that same equation for all I know, but I'm pretty sure there's none there. So see if you can derive. It's just following sort of basic rules of calculus again, but see if you can figure out why that is in fact the gradient of this loss function. And finally, we can also add regularization as well. So we could, just as before, as we did with the support vector machine, we could also add a penalty on, say, the L2 norm of the parameter vector, and that would be a reasonable algorithm to do as well. All right, so here is the solution of logistic regression on our cancer data set. Looks remarkably similar, but not quite the same as the support vector machine. If you notice, I actually have them back to back here. So this is a support vector machine. That's logistic regression. You see the little wiggle there? So this is like 50 years of machine learning progress, right? And also, these two loss functions, right? Here, going from this one to this one. That's also like 50 years of progress right there. Of course, the actual kind of advances that came with support vector machines is that they were developed simultaneously with a different representation of nonlinear functions called kernel functions, which we'll talk about later in class. So support vector machines, though the algorithm itself is quite simple, a lot of their popularity arose precisely because they actually were often bundled with what are called kernel methods, which we'll talk about a little bit later. Is a question there? No, I can't hear. I mean, the reality is, so I'll say why the lines are different. So when I optimize those two loss functions, I get slightly different parameters because they are in fact different loss functions. And in this case, that corresponds to these things. I'll tell you what the actual difference may be of these two loss functions, and I'll highlight that by looking at the actual losses themselves. So with the support vector machine, once you get a loss of, or once your hypothesis times your y value is equal to 1, you don't care about it anymore, right? So you just stop doing anything there then. You stop trying to optimize it anymore. On the other hand, with logistic regression, even though the gradient gets very, very small, it actually never gets 0. There's always a little bit further down you can go, right? And so it turns out this actually causes a notable difference in sort of the optimization side and kind of how these algorithms can behave in certain cases, though I do actually want to more emphasize their similarities over their differences, because the reality is they both are linear on this range. They both go to 0 over here, and one's just kind of a smoother version of the other. Yeah? So the question is, which one usually performs better? And actually, that's not the case. So support vector machines are not actually usually better than logistic regression. The problem is that support vector machines have been, and actually this is a general point I should add too. Support vector machines have been oftentimes conflated with their nonlinear function representation, namely using kernel functions to represent the hypothesis function, whereas logistic regression, oftentimes people just refer to using linear functions, to linear hypothesis classes only. Now, you can use kernel logistic regression too. That's a perfectly valid algorithm. It's just, and we'll talk about that when we talk about kernels too. Sometimes one does better, sometimes another does better. There's a very minor point I'll add, that when you use kernels, because of this function here, support vector machines actually sometimes can be a little bit more efficient computationally to run, because they actually can discard some data. Those data points that have 0 loss, they can actually end up discarding those and not include those in the optimization. But the actual algorithms themselves, there's not that big a difference. They just have a slightly different loss function, and it's very data dependent which one does better over the other. And actually, oftentimes, a squared hinge loss, if you take that hinge loss and square it, that does better than a normal hinge loss. So that's a support vector machine. That sometimes people call it a squared hinge loss support vector machine. But really, these things are not that different. And there's no good sort of rationale for one doing better than the other. That sort of mindset often comes from the fact that people have applied them with certain representation functions that are richer. So nonlinear representations are richer than linear functions. And so people oftentimes just mean that, and they say SVMs are better than logistic regression. And that's not what they actually mean. They shouldn't be meaning that. Again, because we have this sort of breakdown of, to define an algorithm, we need to know the hypothesis function, the loss function, and how we optimize it. And these are only different fundamentally in the loss function. So if you make everything else the same, they're pretty much the same. So actually an important point to keep in mind, because it's one that a lot of people, I think, gloss over. Yeah?
So often the logistic regression is shown with the sigmoid loss function.
Yes.
Which looks like very different from this logistic loss function.
OK, so yeah, so the question was, sometimes the logistic regression is shown in terms of a sigmoid function. But importantly, it's actually not a sigmoid. And if you don't know this, don't worry. Importantly, it's actually not a sigmoid loss function. So this is the loss function of logistic regression. What you're referring to is the fact that you can interpret a sigmoid function. It's actually just this one. It's just this thing here. See a different version of mine. It's just this one here, actually, with a negative sign there. You can interpret that as actually being a probability. So this function here, if you just take the 1 over 1 plus x, actually with a negative sign there, that would be a sigmoid function, it's called. But again, don't worry if you haven't seen that before. It's a number between outputs a number between 0 and 1, which actually can be interpreted as a probability of being positive or negative under this logistic model. Now, importantly, the connection there is that and we'll cover this all in a later lecture when we talk about probabilistic modeling, but the interpretation there is that when you think about this as a probabilistic model and maximize the probability of your observations given your data, you get this logistic loss function out. So it's actually that you get the exact same problem, it's just that it comes up with this other sigmoid there. So I'm not talking about that. I actually want to, because it's honestly just kind of confusing. They're the same, they're so similar, right? And I think it kind of, again, confuses the similarity here. So this is the loss function it optimizes. There are interpretations of it, just like there's a geometric interpretation of support vector machines. But this is the loss function it uses. And this is the difference here, right, between those two loss functions. So hopefully that gets at it. We'll talk about that more in a later lecture on probabilistic modeling. All right, any questions? All right, so now let's just finish up. And I mentioned this before, talking briefly about some libraries for machine learning. So this is how, while I will encourage you, whenever I can, to implement your own algorithms, especially for simple things like support vector machines, the reality is there are a lot of things where you're going to want to use libraries. And many libraries exist for Python, but the most popular being the scikit-learn library. And by all means, you should use it when you can, or when you want to. When you don't want to implement your own version of an algorithm, they have good implementations. If you want to do something quick, by all means, go ahead and use scikit-learn. It's by far the most popular, I would say, machine learning algorithm or machine learning toolkit in Python. And it's usually they have reasonable implementations for many algorithms. They are definitely not the fastest. Certainly. Sometimes they link to other libraries that are sort of more industrial strength when they can. But oftentimes they just have internal implementations that are kind of OK, but they're not great. But they're usually fast enough for sort of small or medium problems. There's not going to be any problem. And you can run a lot of different algorithms very easily because they all have the same interface. And so it's a kind of a nice framework to use. I will say, though, that I do think that people often apply it incorrectly. They use the default functions. For example, the default support vector classifier uses a nonlinear kernel, whereas the support logistic regression uses a linear function. So they're going to look very different. And that makes people think, well, linear regression is much better, or sorry, support machines are much better. And so I think it's important to know, especially because these are not that hard of algorithms. The algorithms are actually very, very short. It's important, I think, to whenever you can, at least know how the backing algorithm works before applying these things kind of in an ad hoc fashion. So, however, you can apply it. Here's the kind of syntax. I went over this last time, but there's 2 different support vector classifiers in there. One called SVC, one called linear SVC. As another historical kind of note, these are actually different in subtle ways. Like one regularizes the bias term or the constant feature. One does not regularize the constant feature. One uses a nonlinear kernel by default. One uses a non-hinge loss by default. It's all very kind of strange. They all use the C parameter. I think actually in general, scikit-learn uses a C parameter, which is the inverse of the regularization parameter. So you're going to take this lambda that was over here, divide by it, and so 1 over lambda equals C there. And there are other fun differences as well, like specifying how many iterations of gradient descent, or actually not even gradient descent, actually something called stochastic gradient descent, which we'll also talk about later when we talk about big data, which you want to run. But there's lots of sort of things here which, again, once you learn what these all are, you can apply it perfectly well. But if you don't know what they are, it can seem very confusing and kind of arbitrary. So I said this before, but I'll just go through it a little bit more step by step here. The nice thing about this is we can actually implement a support vector machine really, really simply, though, right? So this function, and most of this function actually is doing nothing. Most of it is just kind of boilerplate code here. It's really one line of importance, which is this line with the gradient equation there. With 5 lines of code /1, or 6 lines of code /1 line of actual code, you can implement this algorithm here. So what we do here is so X here is our input. It is a vector, it's a matrix of an M by N matrix that contain the examples in the rows of that matrix. That's the same one you have to pass to scikit-learn, by the way. So you actually have to construct that matrix no matter what you're doing. Theta is going to be our parameter vector. We initialize it to be all zeros. We just actually keep things a little faster by pre-computing X times Y with that notation there. Remember from our NumPy lecture that actually scales the rows of Y by X. And then this form here actually computes in matrix, kind of a matrix notation, what the gradient is that I showed on the previous slide. And then you just update the parameters by taking a small step in the gradient direction. And that's a support vector machine right there. So the thing that always actually kind of interests me about this is that these are the vast majority of machine learning algorithms. Maybe I'm wrong. Maybe I just don't know the other fields well enough. But unlike what seems to me to be the case in a lot of computer science disciplines, it's hard to write a database in 5 lines of code. But you actually can write a support vector machine in 5 lines of code. So one of the beautiful things I think about machine learning is that it isn't very long. It's not very verbose. And so because of that, it's often a really good kind of experience to write these things yourself at least once. Then you can go and use the library. Yeah. No, scikit-learn actually does have regularization too. It just specifies it in terms of the C parameter. So the question was, is this thing equivalent to the scikit-learn library without regularization? And no, scikit-learn does regularize here. It's just that it specifies the level of regularization by this term, by C, not by lambda. So if you don't specify a C, it'll set C equal to 1. Yes. I believe this, so there's some differences, minor differences. I mean, linear SVC actually uses an algorithm called stochastic gradient descent, which is not quite the same. SVC will not regularize the bias term, so that there will be no regularization on the last on the constant feature in your matrix. In fact, you don't specify a constant feature oftentimes when you feed in your matrix here to scikit-learn. You don't give it a constant vector. Other than that, they're identical, yeah. So if you were to, what it ends up doing is you would actually only add lambda times theta for all but the last quantity, and then the two would be identical, yeah. And those are minor things anyway, because you'll pretty much get the same answer for large or small values or for small values of the regularization. Oh yes, and also very important. As a highlight, I mentioned this many times, but I mentioned the fact that I'm using these numbers, but I am using -1 and +1 as our class labels, not 0 and 1. If you plug in all my equations, but have y, your true labels being 0 or 1, it will not work. It will give you an incorrect answer. So I do that because I think that the equations are simpler if you use -1 and +1. It's very common to use 0 and 1, especially if you have, by default, the probabilistic interpretation. But I think this is makes the math a lot nicer, makes things look a lot more similar, in fact. So that's what I use. So if you get your y's as 0 or 1, make sure to multiply them by 2 and subtract 1 to convert them between -1 and +1. All right, and finally, this is finally now getting to the nice elements of scikit-learn, is you can try other algorithms, logistic regression being one of them, by just running the exact same function, clf.fit. That's the same thing we did for fitting a support vector machine. But just now instantiating CLF to be a logistic regression classifier instead of a support vector machine classifier. So this is where it does become pretty nice, right? I mean, it is 5 lines of code. You can write code for logistic regression and support vector machine. It would be very simple, right? You would just replace that one gradient line with the one from the slides here. But there's always a chance to make an error on that. You have to tweak it a little bit. This can be nice. So I definitely don't want to dissuade you from using these libraries, but just be aware of what they're doing on the back end. By the way, if you want to, you can also access the parameters for both logistic regression and a support vector machine. And you can do this by the coef_ call. That gives you all the coefficients except for the constant term one, and .intercept gives you the constant term parameter. So you can inspect the actual results of these things and see that they are, yes, in fact, the same as what you get when you run the algorithm yourself. Those 5 lines of code yourself. Actually, I wonder how many lines. Does anyone know how many lines of? Well, no one's going to know this off the top of their head. But check how many lines of code the support vector machine in scikit-learn is. I bet it's longer than 5. A lot of stuff builds up in order to handle a lot of different cases. And I think if you just care about your case, again, you can often make the code much smaller. OK, so that's all for classification. Well, all for now, for purely linear classification until we start talking about nonlinear modeling. Any questions? OK. Let's jump to nonlinear methods. All right. So for this lecture, at least, I'm going to now return from classification to regression. I'll come back to classification at the end of, it'll be next lecture, not this lecture, as well as talk about a few more things in classification. But I want to return back to our regression example, which was this example of predicting the peak energy demand, peak electricity demand in the Pittsburgh area, given some knowledge of the high temperature. So we had this nice plot saying that in the summer months, it seemed at least that the high temperature, the peak demand was driven largely by air conditioning, and so it would increase roughly linearly with temperature. Right? We had this nice plot here, and we fit a line to this data so that we were able to build a model which would predict, given a new high temperature, what is our most likely peak demand, or what is our, I shouldn't use the word most likely here, but what is our peak demand likely to be? We'll talk about probability in those interpretations later. So everything was kind of nice here. But as you might have kind of guessed, I I sort of cheated here. Well, I didn't cheat, but I restricted my domain here substantially by looking only at the summer months, right? Because our model we fit to this, which was kind of a line through this, right, probably would have said that if you just keep going, that for cold enough days, we're going to actually generate electricity as a city, which is probably not true, right? We probably aren't going to. It's probably a point. You can even start to see it happening already here, where you're going to saturate, and you're not going to keep using less and less electricity because people just turn off their air conditioning when it gets to be, maybe 70 or 65 degrees, right? We don't use air conditioning in this temperature range, that being a high temperature. And in fact, now if we just go back and take all the exact same data, which you have in your notebook, and plot all months, we get this shape instead. So this is now all months for the last 6 years of what the high temperature was in Pittsburgh and how much electricity there was consumed by the area as a whole. And as you might imagine, it does not just keep going down in a nice linear fashion here. What happens instead is once you reach about 60 degrees or so, it kind of flattens out. And then a little bit more slowly, but still very noticeably, it kind of creeps up in the other direction, right? This makes sense too, because while most of the heating in Pittsburgh, at least, is not from electricity, it's gas-based, or some people might even have oil here. Mainly gas, though, is what most people have. There is certainly still some people that have like electric heaters. They're going to run more in the winter than the summer, as well as things like maybe lighting. People use more lighting in the winter, right? Because it's dark more often, so you turn on the lights more often. So as you might expect, temperature starts to creep up, demand starts to creep up in the other direction as the temperature gets lower and lower. But still looks actually like a pretty nice function here, right? Looks like there's an obvious pattern about what's going on here. One that you probably couldn't have just guessed purely from your own kind of intuitions. But looking at the data, it's very obvious what's actually going on here. What happened that day, actually? I should look up what day was those outliers there. It'll be interesting to see. Okay. But now, obviously, we have a problem, right? Because if we fit a line to this data, it's inherently not very satisfying, right? We wouldn't say this is a good model of what's going on here. And so the real, in some sense, power of what is called linear regression is that it actually can capture things that are inherently nonlinear. Kind of oddly, but that's the terminology we use. And so I'm going to put here kind of nonlinear in quotes, but at the same time, I also try to actually not use, I guess I just kind of switch between making that hyphenated or not, but apologies for that. I'll try to be more consistent about whether I hyphenate nonlinear or not. Either one is fine. Some certain words, when you use them enough, their hyphenation disappears. Anyway, we'll talk about nonlinear regression. And I'm using nonlinear in quotes here because the algorithm we're going to talk about here is still linear regression, the algorithm. The difference is our hypotheses now, really when it comes down to our features, are not going to be a simple linear function of the raw input data anymore. They themselves are now going to be nonlinear features of the input data. So what we do is actually very simple. What we're going to do is we're going to take our feature vector xi, but instead of just having, say, the high temperature and a constant feature, we're going to have the high temperature constant feature and, say, the high temperature squared. Right? So we're going to add a squared term to our feature vector. And now we're going to use the same hypothesis class as before. In other words, we still have, I'm going to put this up actually at this point. We still have our linear hypothesis function, right? We still have the fact that h theta of x is going to be equal to x, or theta transpose x, which again is equal to sum over all I. I actually use j here. Sum of j equals 1 to n of theta j and xj. Right? So we still have the exact same form. The difference now is that the elements of x here are now themselves squared terms. So it's hopefully apparent that this formulation here with that feature vector would actually capture quadratic functions in the high temperature, right? Because we'd have a linear term, a constant term, as well as a quadratic term in the high temperature. So it's linear. So this is sort of the important character. It's linear in the parameters still linear in theta, but it's nonlinear in the underlying data. So it's nonlinear, where in this case the underlying data is, for instance, what the high temperature actually was. We accomplish that by just taking nonlinear features of the raw input data. And the solution, fortunately, because our solution was just in terms of theta, right? We're just trying to solve for theta here. We're not x is sort of given as input to the algorithm. Our solution remains exactly the same as before. It's just, for example, for least squares, x transpose x inverse, x transpose y. Form that equation. Now with one of the columns being a squared term, we solve it, and we get the solution. OK, so let's see what this looks like. So here is our polynomial features of degree 2 fit to this data. And as you can kind of see, I'm going to say that OK? It's kind of a little bit showing up OK, I guess. This is a quadratic function now that tries to capture this data. And it probably does a little bit better job than a linear function, right? I would say this is a better fit than this one in terms of the actual quality of what it's trying to capture. But it's still not great, right? Because it's still, quadratic functions are you know, around some point, they're always symmetric, right? So they're sort of, not necessarily, actually, sort of, but their slope increases the same amount going in both directions, right? They're sort of in the limit, they're going to be symmetric around some point, and so you know that's not maybe ideal here because we have this obvious case where you know things seem to increase more on that end than on that end, but we don't need to stop at quadratic functions, right? We can add whatever features we want. So I can also add degree 3 polynomials, and I get more and more. Before that, though, I want to just highlight, you know, what code we write to actually do this. So here's the code that will actually create these functions. Haven't actually posted this code yet. I'll post this code too, along with the linear regression one. But the basic idea is pretty simple. We take our feature we care about, like temperature. And here I'm actually doing something a little different from what I talked about before. I'm actually normalizing this, this feature to be between -1 and +1. So I'm taking my x, all my x's, my temperature, sort of my raw underlying data, and I'm scaling it by subtracting off the min and dividing by the max minus the min, and multiplied by 2 and minus 1. That first thing, without the multiply by 2 and divide by 1, that would make these features all scale between 0 and 1. And then scaling it like that will make it scale between -1 and +1. The reason for that is that polynomials are sort of actually, they get numerically unstable very quickly. And so to capture kind of all the, you know, both sides of like a cubic function, and to do so without running into numerical issues, it's a little nicer to normalize like this before you square. So rather than normalization like I talked about last time, where you sort of you know, after the fact normalize each column or row. Here I'm actually doing that before I take the polynomial functions. It just ends up being slightly nicer. You'll get slightly better fits to data, and you can fit, you know, degree 50 polynomials with still you know, reasonable numerical accuracy. I make y, in this case, just my load, and then I actually create a feature vector of x to the I for I in the range from polynomial, you know, going down from polynomial degree by -1 down to 0, effectively. And so that creates a feature vector that is essentially looks like this. You have a big matrix, rather, where your first element has x1 squared, and x, I guess if poly degree is equal to 2 here, then it will have x1 just 1, then it'll have 1, because I do actually include the 0th power in this polynomial, so I don't need to add a special constant feature. And next it'll be x2 squared, x2, and 1. Where I'm kind of abusing notation a little bit here, because I'm saying that x is kind of, x really is this whole thing. X1 is really this whole thing, but x1 here would be, I guess, just the raw underlying temperature. But this call here just creates a matrix like that. And then the nice thing, of course, here is that my actual solution for theta is exactly the same as before. I just call linear.solve x transpose x x transpose x times x, which is numpy is xt dot x, and then xt dot y. If I want to visualize what my function looks like, so like how I plotted this green line here, I did that by creating a linear space with the linspace command between some lower limit and some upper limit, with say like 1,000 points in between. I also scaled that one by the same function I scaled the one above, and then I created a similar set of polynomials for that. And then I got my predictions just by saying, taking my new matrix here and multiplying that by theta. So that hopefully makes it a little bit more concrete what I mean when I say create a polynomial feature vector, because it really isn't that hard. It's a couple lines of Python code. And by the way, you have to do this even with scikit-learn. If you want to use these features, you would have to still create them that way. You couldn't. It would just be this one line you would replace, and it would actually this one theta equals line, and it would actually be a longer line anyway than that. So I am going to advocate that everyone for linear regression always just solves it that way, at least for small problems. Some questions? Don't worry about getting this all right now. It's online, and I will release the code for it too, so you can look through it later and make sure it all works. But this is how you create things like nonlinear features. All right, so that is a degree 2 polynomial. No reason to stop there, though. Let's do a degree 3 polynomial. Looks a little bit better, right? Now we kind of should capture the two different directions here. At least for the most part, maybe it kind of collapses on that side, but it looks actually pretty reasonable here. And we can keep going. So here's a degree 4 polynomial. Not too much change, but it was actually kind of rightly getting up that tail here. I should add, you can't really ascribe too much meaning to what happens outside the range of data points you've seen so far. So the fact is that this kind of tails off, way down here isn't actually that big of a deal because it doesn't know any data points outside. So all it can do is fit the data points that fit the range of data it's seen so far. So you're all using kind of your own knowledge to say, well, I know that when things get even colder, it'll just keep going that way. That's harder for an algorithm to really know. Not impossible, but a little bit harder. But let's just keep going. So here's a degree 10 polynomial. Actually looks still pretty good. I would argue that in the data range this actually captures, this is a pretty good function, right? A pretty nice function that fits reasonably well to that data. But we can go a little overboard here too. So here's now a degree 50 polynomial. And we've finally gotten to the point where we're a little bit exaggerated here. So what is happening here? Yes, I heard the word overfitting. That's correct. What's happening here is that this is actually a really good function for fitting this data in terms of the least of the squared error loss. And the reason for that is especially like over here. So look at over here. So this function hits those data points exactly, right? There's all those ones on the left there. It's getting them exactly. So it's actually passing through those points. There's points that look kind of like this. I should just do it. Something like that. And it goes, like this. Something like that, right? With really, really big numbers there, but it actually, I drew this horribly, of course. It hits it exactly. So the function goes through, hits this point, comes down, hits that point, goes up, hits that point. In other words, at these points, this function has 0 squared loss error, right? The loss is 0 at those points over there. It's not 0 here, and it actually can't be 0 completely ever because we happen to know in this case that there are some repeated high temperatures. So the same high temperature will have multiple different demands, so you can never get 0 loss there. But if you have points that are all separate as in their inputs, you actually could get zero loss by having a high enough degree polynomial. And I'll just emphasize this actually kind of from a linear algebra perspective. If this doesn't make sense, don't worry too much. Conceptually, hopefully it kind of makes sense that, if you have a high enough degree polynomial, you can kind of fit the points exactly. But what's actually happening here from a linear algebra standpoint, I think is very interesting. So what was happening here is that let's suppose that our number of, oh, I don't need a new slide yet. Let's suppose our number of data points is equal to our number of features. Well, this means that our matrix here, X, is actually a square matrix. Remember, these are always matrices in M by N. So we have M examples and N features. But if those are the same, if we have as many features as examples, this is actually a square matrix. Okay? And square matrices, assuming they are invertible, and we'll assume it's invertible, that actually, for people that know about this, that requires that these features have to be independent. One can't be a linear combination of some other ones. But assuming that, they have to be linearly independent. But assuming that is the case, then we actually can simplify our equations here. We know that theta equals x transpose x inverse x transpose y. And in general, we cannot simplify this anymore because this term here is, while this term, the x transpose x is square, and we can invert it, x itself is not square, so we can't really form the inverse of that. But when x is square, we can actually distribute n invertible. We can actually distribute this inverse inside this multiplication here. And what we get is we get this equals, and I had this on one slide, but when you invert matrices, you actually flip their order. And the inverse of the transpose is the same as the transpose of an inverse. So you can call them kind of, doesn't matter what order you do those in. So this gives us actually x inverse, that's the second term here inverted, times x inverse transpose. I'll just write it like that because it doesn't matter what order we do it in. Times x transpose times y. These two terms cancel here. That becomes just the identity. So this thing equals x inverse y. And assuming x is, again, invertible, this will also actually imply that that x times theta with this solution is equal to y. Right? In other words, our prediction, which is just the row, the elements of this x times theta vector, are always equal to our outputs y. So that's kind of that is exactly why kind of mathematically, I guess you have to also prove mathematically why polynomials are linearly independent, which takes a little bit more work, but this is mathematically why a high enough degree polynomial is actually would be the number of, the degree has to be the number of points minus 1, because you have the constant feature 2. But that degree polynomial can actually always pass exactly through this many points, assuming the points are not like what we have, but actually are all have separate underlying x, or underlying temperatures, say. Okay, so now let's talk about a little bit more rigorously, maybe, what's happening here. So I heard the term overfitting mentioned, and now we'll finally, after teasing it many times before, I'm actually going to finally try to define what this actually is and how we might actually start to get some sense of how to avoid these things. So the problem with our canonical machine learning algorithm, remember that is minimizing over theta the sum of losses on our data set, right? The problem here is that this is not actually what we care about. Right? What we care about is not just how well we do at predicting the data we've already seen. That's not a very useful trick, right? If you can someone gives you a data set and you can definitely say, for everything you've already seen, I know exactly what to predict there. That's not too interesting. What we actually care about is how well our function is going to generalize to new inputs, right? So if we get some data point we haven't seen before, how well is it going to predict on that data point? And this is a term or a quantity called the generalization performance or generalization error of a learning algorithm. So in the example we've seen so far, the higher degree polynomials overfitted or exhibited what we call overfitting. So in other words, they had very low error on the data set we trained them on, but they had relatively high error on the actual their generalization error was relatively high. And that's kind of what we mean by overfitting. We mean that on the data we train the system on, we get very low loss, but when we sample some new data, we expect the loss to actually be quite high. And the sort of the cartoon version of this would be a plot like this, where I'm on the y-axis here, I'm labeling the loss, and on the x-axis, I'm labeling the complexity of the model. So the loss, if our model has, I guess, 0 complexity, right? That would be something like we always predict just 0 for our prediction, no matter what. That won't have infinite loss, right? That will have some finite loss that you get if you just make a silly prediction for every single example, say 0. As we increase the complexity of the model and we optimize these models using machine learning, the training error, that is the performance of our algorithm on the data we're training it on, is going to decrease. And for a while, if we have anything like reasonable, like an algorithm or any sort of reasonable data set, for a while, generalization performance will also decrease. So it'll also start going down. But at a certain point, whereas the training error will always keep getting lower and lower. So actually, this is a fact that I'll kind of hammer home a few times. But generalization of training error, no matter how much you increase complexity, will always go lower and lower, which of course makes sense, right? Because we have a bigger model class than we had before. So if we could do, say, this is what we're actually optimizing in our model. So if we could do this, get this loss with some complexity of model, we can get this loss with a more complex model. You can only get better as you increase complexity. That is not true for generalization, though, because for generalization, if you actually keep going, you will start to now overfit to your training set, and you will actually generalize worse to new examples. Of course, it's oftentimes difficult to quantify kind of this true generalization error. It's kind of this quantity of in expectation over some new distribution. What do you really expect to get? And so the way we do this instead is with a method called holdout cross-validation. So this is probably pretty familiar, or maybe familiar to a lot of you. The idea is actually very, very simple. The idea is even though it is hard to approximate, or not hard to approximate, it's hard to compute the exact true generalization performance. This would be, over the true distribution of examples. We can approximate it using a finite data set. This is a technique called holdout cross-validation. The idea is very simple, and probably what all of you have been kind of expecting all along with all this. Exactly like you would think, you take all your data and you split it into a training set and what's called a holdout or a cross-validation set. Right? And so you take that holdout cross-validation set, or rather, maybe you take the training set, and you train, as you might imagine from its name, you train the algorithm on the training set. So in the case of least squares, for instance, I will compute this equation, i.e. my parameters theta. And that's the same whether you use least squares or not. You can use any other algorithm as well. But I'll compute my parameters that minimize my loss function on the training set. So in this case, these x's would only contain the rows corresponding to those examples in the training set. Then, once you're done, you don't evaluate the performance of the algorithm on the training set. You evaluate it on the holdout set. So you evaluate it as how well it performs on the data which you did not train it on. So again, all kind of what you would expect to do. So let's just go through the code now that actually does this. As a pretty simple example again. We're now going to use randomized selections. Whenever you use a randomized function, it's always good to initialize the random seed so you can run the exact same thing again. Otherwise, you might get a great result, and you go back and you change your random seed, and you can't actually ever recover it. So you always get in the habit of sort of setting your random seed to be something at the beginning. I'm going to use the random.permutation call to generate a random permutation. That's an ordering of the numbers between 1 and m, which is the size of our data set, based upon our random seed. And then I'm going to select indices of our training set and holdout set just by looking at the first 70% of that permutation and the last 70% of that permutation. Now, I should probably mention here that doing it this way for the case I'm talking about here, which is this high temperature peak demand prediction task, is actually kind of mathematically wrong. The reason it's wrong, and I'll mention this again briefly later, is that what we're literally doing here is we're using the future to predict the past, right? Because we're randomizing over all dates. Remember, each sort of entry, each row in that matrix corresponds to a day. I'm selecting some random subset, so that means I'm going to train on days that are kind of forward in time and use that algorithm that use those parameters I've learned to train on days before that, which is probably a bad idea. You probably want to split things based according to time, so you're not actually doing that. But I'll ignore that for now. I'll assume the data kind of is independent in this sense, and so that I can actually do this. So in the first kind of code block there, what I'm doing is creating these random permutations. In the second code block, I am scaling my data to the proper range and creating the x and the sort of the raw underlying x and y variables. And the only point I want to highlight here is that my choice here was to actually compute the scaling based only upon the training data, not upon the holdout data. So I actually normalize only based upon the training data. That can actually go either way. It's not actually wrong to use your holdout data also to normalize. The reason for that is that you can imagine, in machine learning, you sort of assume that you have access to the inputs for the data you're trying to evaluate as well as your training data. And so I can always kind of use all my data to normalize my inputs. But I'm making this choice here because it's a little bit more common to only use your training data to normalize the inputs. In this case, again, because we're using polynomials here, I'm normalizing them to be between -1 and +1. And then finally, I create my feature vector. I train my least square, optimize my least squares parameters theta, and I can evaluate train and cross-validation error. I should probably call this cross-validation and train loss, because it really is the squared loss. In fact, it's the average square loss on each example, over each examples in the training set or in the cross-validation set. And that's just sort of how I do it. So now we're actually getting to be, I certainly can abbreviate this a little bit, but this is actually somewhat brief in terms of the code. And this kind of stuff actually, scikit-learn is very good at doing. So it actually is very nice, especially when you have more complex cross-validation procedures. It is admittedly quite nice at doing these breakdowns. They're all very sort of formulaic. There isn't much more to it. But this, maybe I think you will have to do it once in the homework, in fact. But after that, you don't have to do it anymore. Was a question somewhere? Yeah.
In the beginning of the program, why you take 0.7 of the last array?
Yeah.
No, of the same code. So you want to split 70% and 30%?
Yep.
But not 70% and 70%.
70% is 140%, so that would be hard, right?
No, but in the code you have you multiply by 0.7 in the both lines, in the third and the first.
Yeah, okay, so right. So the question was, you're multiplying by 0.7 in both cases here. So what I'm doing here is that I am putting this is a slice to that location at 70%, and this is a slice from everything else after the 70% location. Yeah. So I'm doing 70-30 is the breakdown here. Yeah. All right, any more questions? right, so just a little bit of terminology now. I'll also keep referring to this, so I want to just define these terms. I'm going to call, and I already use this term in fact, but I'm going to call variables like theta. These are the variables that I use that I use the training set to optimize over. Those are called my parameters. And those are called the parameters of the machine learning algorithm. Every other kind of design variable we have, so that would include things like the number of features we use, right? What degree of polynomial we use to create our feature vector. Also things like what value of regularization parameter we use. Those are collectively referred to as hyperparameters. And the idea of cross-validation, holdout cross-validation, is that we're going to use a training set to train our parameters, to find the parameters that minimize our loss on the training set. On the other hand, we're going to use our holdout set or our cross-validation set to pick our hyperparameters. These are those meta-level parameters that actually specify the nature of the problem we're solving in the parameter optimization. And we're going to use the holdout set to pick those. So this is what it looks like on our data here. I've here created a 70-30 split of our electrical consumption data set. In blue, I'm showing, so that this is exactly the same data as I had here. It's just now I'm coding it either blue or green. Blue if it's in the training set, or green if it's in the holdout set. And what we're going to do is we're going to train our algorithm only on the blue points here, and then evaluate how much of a loss it has, not on those points. Well, you want to do that one too, so you want to evaluate it on those points, but also on the loss it suffers on the green points. And here is what this looks like. So this is not quite the cartoon, but actually pretty close to the cartoon picture in this case. So what I'm showing here is I'm showing the degree of the polynomial, and I'm showing also the average squared loss. That's the average loss we suffer per example. And I'm here normalizing by the, but I'm showing the average loss so that we're actually normalizing by, the size of our training set and the size of our holdout set. So these numbers are exactly comparable. But the basic idea here is that when we start off, this point here would be a degree 0 polynomial. In other words, it's a constant function. So for a constant function, you would expect these things would perform about the same, right? Because your mean of your, which is actually, interestingly enough, and you should get familiar with this, but if you run least squares with only a constant feature, you will actually just be predicting the mean of your data set. So if you look at this equation here, when this is just one constant feature, you would get the sum of the y's here, and you would get the sum of these things squared. In other words, that would be 1 over just the average value of the y's. So a little aside there. So over here, they're both pretty similar. And they actually both go down for a little bit, because as you would imagine, a linear function is better than a constant function. A quadratic function is better than a linear function or a constant function. And for a while, it looks OK. But then pretty quickly, we start getting clearly to be in this overfitting regime, where I'm even plotting the loss here on a log scale. So very quickly, we kind of get astronomically high losses in terms of our actual error. Not on the training set, because those we know are actually just going to keep going down. But on our holdout set, we very quickly start getting very, very bad performance. And as you would imagine, right? Because so we have a loss of like an average loss of like 10 to the 8 on our degree 50 polynomial, and that kind of jives with what you see here, where especially if I were to leave out one of those points and fit on everything else and see how we did on that one held out point, that would be pretty bad, right? It would probably shoot off and miss one point and do really, really bad. I think actually what's happening here is that we missed one of the last ones. And so think of a point that's like right next to that point that's hidden from the training. It's getting a really, really bad value for that. And so this is what it looks like. We can zoom in a little bit to get a little bit more reasonable view of what's happening in kind of the range we really care about. And that is that clearly quadratic is better than linear, cubic is better than quadratic. After that, after cubic, actually there is not that much of an improvement. Maybe degree 6 is slightly better if you really want to be, precise. But after about a cubic polynomial, you don't get too much gain by going higher until eventually you go much worse by getting higher. So this is the actual results on this data set of what happens when I vary the degree of the polynomial and look at holdout error versus training error. Yeah? So the question is, why is actually the training set higher than the cross-validation set? And that's just random noise. So in general, you're absolutely right. If you're truly talking about generalization error versus training error, the training error will be lower because you are actually optimizing that. But with a holdout set, there's always an approximation involved, right? And so what I think is happening here, I can actually look at what this data says. Yeah. So what's happening here is that there are certain points, like those outliers in blue there, that are just hard to approximate for any classifier. You're never going to get that, in fact, because you have other points probably on that exact same point. And so for random reasons, your training error is slightly higher than your holdout error. That is not a statistical effect. That is a random effect. And as you select more folds, you will tend to have, and more randomizations, you will tend to have holdout error that is slightly higher than your training error, but both will happen, one being higher than the other. Over here, this is certainly not a random effect. This is the actual effect of overfitting to your data. And it starts happening around degree 20, but probably, honestly, before then, you probably want to not go too high, because the advantage is so small too, right? All right, any other questions? All right, I want to finish maybe, no, I have a few more. I have a little more time. I want to mention a few variants of cross-validation. In fact, these are so common that that oftentimes people think that what I mean by cross-validation is actually one of these things. There is another type of cross-validation called k-fold cross-validation. And the idea here is that instead of splitting our data just into a training and a validation set, the problem with that is that there may be, especially when we have a small finite data set, it's kind of a shame to kind of use part of our data set only for training and part of it only for testing, right? I mean, what if we wanted to test on another example? Why do we pick that particular split? This can be an actual issue when your data sets are small and you really want to get a good sense of sort of what's the best estimate I can get of my likely error. Now I should add that statistically, k-fold cross-validation actually does not have that much advantage over just single holdout set cross-validation. The theory, in other words, for this is not that much better for holdout cross-validation, but it's actually a little bit, it's still very common because it seems like in practice it tends to work pretty well. So the idea is very simple. The idea is we're going to take all our data and we're going to divide it into multiple what are called folds. So folds are just disjoint subsets of the data where what we're going to do is we're going to divide it into k different folds and then repeat k times. We're going to train on all but one of these folds and test on the one remaining fold. So in the first iteration, I would train, say, on folds 2 through k, test on fold 1. Next iteration, I would train on fold 1, 3 to fold k, and test on fold 2, etc., up until I'm just training on data up until fold k, and then testing on fold k. And the nice thing here is that in this process, every sample in your data set gets to be in the holdout set once, right? It always gets its turn in the holdout set, which seems kind of fair, right? Because if you have one really bad example, you should still kind of think, well, I'm going to really have different performance based upon whether I just randomly choose to have that example in my training set or my holdout set. Maybe I want to actually just make sure that it gets kind of, everything's going to get its fair chance. And then we're going to report the average error over all the held out folds. By the way, there's a little bit of, people do it both ways. Some people will compute an average error for each fold and then average those. or you can just compute the actual errors on each holdout set and take the errors of the average of all those errors. So it doesn't really matter because they're usually about the same size, but just be aware that you can do it both ways. And this is a very, very popular method, to the point where I tell people to use holdout cross-validation, and they use this instead. They just assume this is what cross-validation is. But cross-validation actually is just a general procedure of taking some set of your data out, training on the rest of it, and then evaluating on that held out set. This is one way of doing that. And for example, scikit-learn provides very nice ways of building these holdout sets and running k-fold cross-validation. Okay, so I finally want to just mention a few last variants here before I move on to our next topic, which I'll get a little bit started with next this time. And those are the following things. So another term you may come across sometime is called leave one out cross-validation. This is sort of the extreme example of k-fold cross-validation, where k is equal to your number of samples. In other words, k equals m. And when you do this, what you're actually doing is you're training your classifier on everything except one example, and then testing on that one held out example, right? So it's kind of the most extreme case. Now, you should look this up if you're curious. This seems like a great idea, right? Like this is the best way you could possibly evaluate things, seemingly, but it seems really expensive too, right? Because I have to train m different classifiers. One very nice thing is that actually, somewhat surprisingly, this is a feature of least squares in particular, but for least squares, it turns out you can actually compute the leave one out cross-validation error in the exact same big O complexity as you just compute the least squares solution. It's somewhat surprising. There's actually a formula for it, which involves some sort of linear algebra tricks to basically eliminate one element from these matrices here and just get an update very efficiently, and it simplifies to be a very nice equation for this. So it actually requires not really any more effort than just running least squares. Also, kind of surprisingly, is that actually this often ends up being not that good an idea. The problem here is that although in some sense you're doing the best thing, because I'm training on everything but one example, testing on that one example, the problem with that is that my different classifiers, because they only differ by two examples, right? So when I train on all but one and all but another, those two problems have all but two examples in common. So it turns out you actually get a lot of correlation in your essentially learned parameters over the different folds. And this actually oftentimes gives you a worse estimate, surprisingly, but it actually can give you a worse estimate of the true generalization error in practice than k-fold cross-validation. So it's not always the case, but sometimes the case, kind of interestingly, that this is not what you want to do, even though it seems so nice. Another word you may hear sometimes are things like stratified k-fold cross-validation, or even just stratified cross-validation in general. Stratified here just means that if, for example, you have a classification task and you have some portion of positive and negative examples, that you keep those proportions the same in your training set and in your holdout set. Right? So if I have an imbalanced data set, say, with 5% positive examples and 95% negative examples, I want to approximately keep that same balance in my training set and in my validation set. That's what the stratified means there. Though it actually does not have to be the class either. It could be any feature that you want to keep evenly distributed over training and testing. You'd want to do it this way. And finally, as a general sort of word of warning, you do not always want to use k-fold cross-validation. So even if you can do it, and have the computation to do it, sometimes actually other cross-validation techniques are going to be far better than k-fold cross-validation. For example, one example I gave already was time series data, right? Where you actually want to, in any sort of real domain in time series analysis, you're going to be predicting things that haven't happened yet, right? You're going to be predicting the future based upon the past. And so if you, in your training, use a future example to predict a past example in your holdout set, that's actually violating causality, right? Because you might be using information from the future to do a better job of predicting the past. People do this a lot with like stock data. When you see a lot of class projects that deal with stock data and they run this, and you know, it's probably a bad idea to do this. You can do it in a lot of very subtle ways too, right? So when you have a time series problem, you really should probably be training on past to a certain point, and then testing on or evaluating on the future after a certain point. And you can't do that with k-fold cross-validation because every example has to be once in the training in the test set. Okay, any questions there? Yeah. What's a good way? The question was, what's a good way to choose k? Choose 5 or 10. Easy. There's no real reason. Make it so that it's big enough so that you can have a substantial training set and you still can run enough examples in your test set and it isn't too slow. And 5 or 10 are nice round numbers, so that's what people use. All right, so before I end, I'm just going to talk briefly now about regularization. So we've seen, we actually have mentioned this already, but now I actually want, with sort of this discussion in mind now, I really want to return and talk about regularization in a lot more detail. So we've seen that the degree of the polynomial that we're approximating these functions with acts as kind of a natural measure for the complexity of a function we're thinking about, right? So, you know, higher degree polynomials are more complex functions. But it turns out that fitting these high degree polynomials to data also requires that we let the coefficients on those high degree terms be very large. So the way we get, so do I have a later figure? No, I don't have a later figure. I should put that in. The way we get figures like this, sorry for skipping back so far. The way we get figures like this is that we need to pick sort of very large and very oftentimes sort of alternating sign coefficients for these polynomials such that we exactly hit a certain point. Because when you have really big polynomials, you have a lot of representational power here. And in order to kind of make sure that we're hitting exactly a large number of points, you end up needing very large weights of the polynomials. You know, one to shoot you off way up this way, another one to go off way off this way, etc. Kind of, you know, make sure that you hit every single point exactly. And in fact, if we look at the data on this problem, if we train a least squares classifier on this task, our first 4 coefficients here are negative 3.8 times 10 to the 6, 7.6 times 10 to the 6, negative, or sorry, not negative, but 3.94 times to the 6, negative 2.6 times 10 to the 7th. They're really big numbers. And that's actually how we are getting this polynomial to hit those points exactly. Remember, the numbers are scaled between 0 and 1. So if we just have like small things, they're going to look basically like still pretty smooth functions, right, with small coefficients. And this suggests another way to control model complexity, which is exactly the regularization idea we talked about earlier, but now discussed kind of in with a lot more context to it. So the idea, which I introduced last time, was that instead of just minimizing a loss function, we actually minimize a loss function plus a regularization term, which penalizes large entries of our parameters theta. Okay. Which hopefully makes sense, right? Because if now we're talking about not just minimizing one thing, but minimizing kind of a trade-off, right? Because if we have a really big value of theta, we need a really big value of theta to get that loss, you know, a little bit smaller to hit certain points exactly. We probably wouldn't bother with that too much if it makes our parameters too big, right? Because that would sort of increase the second term in the loss for some gains in the first term. And so this formulation really trades off, depending on our choice for lambda here. It trades off between picking a very potentially large weights that get as low error as possible. This would be the choice of lambda equals 0, no regularization, versus in the other extreme, we could actually pick lambda to be infinite. And if lambda is infinite, then we're definitely just going to choose theta equal to 0, right? Because everything, any small deviation from that would give us infinite total objective here. And theta equals 0 will not give us infinite loss. It will just give us some really bad loss, right? So we actually want to pick some sort of intermediate value, and we can sweep out a whole path of possible values by varying lambda between 0 and between infinity. So that's what I'm going to talk about more next time. We'll talk about also how we evaluate these algorithms, and then also briefly, because again, it's exactly the same, talk about classification and how we apply these nonlinear methods to classification as well. All right.